What are we doing? Section 6.3 continued. 6.3 continued. So we're talking about sines, rather graphs of sines and cosines functions. So just as a quick reminder, if I have, again, I always hesitate to write how to write it down algebraically because the book just it just makes this really dumb decision to use x as the domain variable for all of them. But anyways, so if I have y equals sine of x, it has period 2 pi, and I'm going to write something else down that I may not have explicitly stated before, but 0 to 2 pi is a good choice of interval. Now, what do I mean by that? That means that I get to see nicely a whole period of sine in that interval. Now, of course I do. If it has period 2 pi, what's the size of this interval? Well, it's from 0 to 2 pi, so it's size 2 pi, right? If it had a size, it would be size 2 pi. So this doesn't really seem necessary to point out here, but when you start shifting these things left or right, then it's helpful to point out the interval where you're going to graph it. Let me go ahead and graph this, by the way. So one period would just be an appropriate, good choice of interval would be 0 to 2 pi. So of course here's 0. And if I'm graphing a straight up sine function, I'm going to put my 2 pi out here, and then I'm going to have pi marked and also the half pi's, pi on 2 and 3 pi on 2. Those 4 points there being marked. And then I'm also going to have my amplitude, which for a base sine function, its amplitude is just 1. So it's just its maximum value is 1 and its minimum value is -1. At 0, we're starting at 0 for the sine function. Then it goes up and hits its maximum at pi on 2, right? Because this is the sine is the y values on the unit circle. Just real quick again, here we go. Here's the unit circle. So if that's the pi on 2 right there, right? Well, first of all, here's 0, right? What's the y value at this point? It's 0, so that's why we start at 0. And then here, let me go ahead and put the whole point there. What's the y value here? This is a pi on 2 angle, right? Pi on 2 gets us to this axis. That's the y value is 1. Now I go back over here. That coordinate point is -1, 0. What angle is that? That's pi. That's pi. And what's the y value? Well, it's back at 0. Okay, now 3 pi on 2 gets me down here. Where that coordinate point is 0, -1. What's the y value? It's -1. So at 3 pi on 2, sine is down here at -1. And then finally it comes back all the way around to 2 pi angle, and the y value is back at 0. So that's the general shape. Cosine. And then y equals, no, sorry, that's the general shape of sine. Y equals cosine x also has period 2 pi. And 0 to 2 pi is a good interval. Notice I'm putting brackets around the interval because we're allowed, we can pick 0 and 2 pi. Those are legitimate. I don't need to put parentheses around them, right? Those are included. Is a good choice of interval. And now when I'm drawing my cosine graph, set everything up the same way with my 1, the amplitude's still 1, so the extreme values in the y-axis or the vertical axis is 1 and -1. And then I go to pi on 2, pi. You always want to split it up into these 4 values, well 5 if you include 0. these 5 values, because that's going to show you the extreme values that this thing hits, and it's going to get a whole rotation of it. And remember that at each of these, we're going to plot at the x values on the unit circle. So it starts off at t equals 0, or rather, the angle, I'll say, is 0. The x value is 1, so I'm up here. Now the next x value is 0, so I'm just going around the unit circle. Next x value is -1. Next x value is 0. Next x value is back at 1. So we're getting this part of getting like a different chunk of the cosine curve, but this is one period of the cosine curve there on an interval 0 to 2 pi. Okay, so that's just a recap. That's like 6.2, beginning of 6.2, right? Or maybe not, I can't remember. I'm kind of out of it right now. So maybe this was the beginning of 6.3. But anyways, there it is. Just a nice recap of sine and cosine, at least for one period of them. We also talked about transforming them, right? We talked about transforming them, and we were kind of in the middle of that discussion. So we talked about like scooting them left or right, and also adjusting their amplitude, and also adjusting their period, aka like how squished or stretched they are. So I think we left off, well, let me write this down first. Let's kind of sum this all back up. Y equals a sine of k times x minus b, and then a similar, just the same exact thing for cosine. So written this way, they have amplitude A, well, absolute value of A. So if A is negative, we just say, like if it was a -2, we just say its amplitude is 2. They have period 2 pi, that's the base period, right? 2 pi for these functions is the base period, but then divided by whatever that number might be, because that's that compression, right? K here is compressing the period from, unless k is a fraction less than 1, and then if you divide by it, then it's stretching it, right? So it's working the same way it did in 112, where when you multiply inside of a function, that's gonna, if it's bigger than 1, you're compressing the function horizontally, and if it's smaller than 1, like a fraction smaller than 1, you're stretching the function horizontally. And that's what's going on here. And then we had the horizontal shifting, so these have amplitude, that period, and B. Horizontal shift B. If it's minus B, then it's a shift to the right, like minus pi on 4 would be a shift to the right by pi on 4, plus pi on 4 would be shifting left. Okay, so now we're picking up in example 3. I believe I left off like in the middle of example 3. I'd already done part A, but I'm just going to redo it because it's a good review. Y equal, and plus you can just skip all of this in the video if you already know how to do all this. I'm going to ask you to graph this. Oh, the instructions are graph. Of course they are. That's going to be the instructions for like every example, pretty much. It's going to have to do with graphing the functions for the rest of this section and the next. Okay, and I'll go ahead and write B down as well. All right, so all this is a sine function that has been shifted right by pi on 3, and this one is a sine function that's been shifted left by pi on 6. So for the solution for part A, I'm going to go ahead and say, I'm just going to say what I just said, but I'm going to write it down. So this is I don't remember how I did it last time, but let's see if we can get it cleaned up a little bit. The hardest part really is deciding like what points are going to be on that x-axis when you're shifting left or right. So let me see if I can make that a bit clearer here. First of all, my new interval where I'm going to graph this thing is not going to be 0 to 2 pi anymore. It's going to be pi on 3 to 7 pi on 3. And where is that coming from? I guess since I'm in a recorded lecture and I have more time to do these things, then I can go ahead and point this out. It's coming from the original base period for, a sine function, but it's shifted right by pi on 3. So I'm literally adding pi on 3 to both of these because I'm shifting it right. So of course this one's easier, right? That's just pi on 3. And then a little bit of common denominator will get you where you need to be here, right? 2 pi is the same as 6 pi over 3. 6 pi over 3 plus 1 pi over 3, that's where that 7 pi over 3 is coming from. So that's the new interval where I'm going to be graphing this thing instead of just 0 to 2 pi. I also would like to find the other where the other points should be, because now I know where my beginning point is going to be and my last point is going to be. So if I graph this, let's see if I can get a picture to work with. First of all, let's see what all can I fit on here without having to think too much. Well, I know my amplitude is unchanged, so those y values are going to be -1 to 1. So my first 0 spot is going to be at pi on 3, which I'll just sort of put there, pi on 3. And I know that there should be a 7 pi on 3 out here, right? But so how does it go? There should be how many points? It starts at 0, then it hits the next one, it goes up, and then it comes back to 0, and then it hits -1, and then it's going to come back to rest at 7 pi on 3. That'll be it. So there should be 3 in between, like 5 total, right? 5 total increments here, little increments going from 0, 1, 0, -1, and then back to 0 to get a full rotation. So I need to figure out what these things are going to be in the middle here. I don't remember how I did it last time, but I think this might be slightly different. But just consider this. Each of these little intervals are going to be a half pi away from each other, because I'm just taking where they were from 0 to pi on 2 to pi, pi to 3 pi on 2, 3 pi on 2 to 2 pi. Each of those little chunks are a pi on 2 away from each other. I'm just taking that relationship and scooting it to the right a little bit. So the difference between these should still be pi on 2. So what I'm going to do to find each of these is I'm going to take pi on 3, that starting point, my starting point, and I'm going to add pi on 2 to it. Okay, so that'll be 2 pi on 6 plus 3 pi on 6. That's giving me 5 pi on 6. That's going to be this point. Potentially a fair bit of side work coming just to get these points labeled here. The next one, just adding pi on 2 to that, so 5 pi on 6 plus pi on 2. That's 5 pi on 6 plus 3 pi on 6. That's 8 pi on 6, which reduces to 4 pi on 3. Okay, that's that point right there. That was originally just pi, right? For the original base sine graph, that was just pi, but it shifted to the right by pi on 3, so does it make sense that it went from pi to 4 pi on 3? Well, yeah, because pi plus pi on 3 is 4 pi on 3. I think that's how I found them last time. I just took each one where they were and added pi on 3 to them. So I'm doing it slightly different here, but it's going to get us to the same place. So now I'm going to take this one. I'm saying, okay, this little distance between them should be a half pi. So I'll do 4 pi on 3 plus pi on 2 again, just adding that distance between them. It's going to be 4 pi on, let's see, that'll be 8 pi on 6 plus 3 pi on 6, so I'm getting 11 pi on 6. Oh, I shouldn't have done this in red because I wanted to do my curve in red. I guess I'll do my curve in like a different color. And then finally, now I already know what the last one is, but just to show you, like 11 pi on 6 plus another pi on 2 will end up being 11 pi on 6 plus 3 pi on 6, which is 14 pi on 6. But you see that reduces, that is 7 pi on 3, just pulling a 2 out of both of those. So the last one is not necessary because I already noted that from adjusting my whole interval. When I adjust the interval up front, that immediately gets me those two outer values, the smallest one and the biggest one. All right, now I'm ready to graph my sine function, starting here at 0. So it's just the same shape as a regular sine function, just scoot it over. There it is. Like literally just taking the axis and like scooting it over by pi on 3. That's all that this function was. And if you, since I don't have it written down, just so you remember, the function was y equals sine of x minus pi on 3. There it is. And that's one period of it. One cycle, you could say. All right. Let's do that part B. So let me say this is oh, you should have it written down, but just in case you don't, it's sine of x plus pi on 6. So this is a sine function. When you're writing, I should have done this earlier. When you're writing sine in words like this, you should spell it out S-I-N-E. That's the full, like that's how you spell sine. We abbreviate it S-I-N for function notation, but when you're writing it in words, you should say it like that. This is a sine function graph shifted, let's see, what was it? Plus, right? So left by pi on 6. All right, cool. So what's my new interval? So my new interval is not 0 to 2 pi anymore. It's going to be negative pi on 6, right, to 11 pi on 6. Where is that coming from? Well, remember my classic interval for the sine function is 0 to 2 pi, but I'm shifting left by pi on 6. So I'm going to take each of these and I'm going to subtract pi on 6 from both of them. Because why am I subtracting? Because I'm going left. And then that's going to give me 0 minus pi on 6, excuse me, is negative pi on 6. And then this will be 7 pi on 6. You know, that'll be, no, what am I saying? What did I just say? No, it's not 7. 12 pi on 6 minus pi on 6. So that'll be 11 pi on 6. There we go. That's where that's coming from. All right, good. So now I can start drawing the picture. I know these extreme values, let's see, I'll use the same color setup that I did last time. These extreme values are going to be in, or when I say extreme values, I mean, they're not extreme. What I mean is the outer edges of my interval is going to be negative pi on 6, which I'll just kind of put there, and 11 pi on 6. which is somewhere out here, but I'm not going to write it down yet because I want to make sure my tick marks are evenly spaced. How many tick marks should I have? Well, I should have 5 total, right? 5 total, so I'll put one there. That's 2, 3, 4, 5. Okay, so there's 11 pi on 6. Got to figure out what these are in between. What are my bounds on my y values? Well, just -1 to 1, because the amplitude of this function, by the way, the function we're graphing is just the sine function with a plus pi on 6 inside. So nothing happening to its amplitude. Its amplitude is still going to be 1. And without even graphing, without even labeling these intervals, I know what sine does, right? It's 0, and then it goes up to 1. So hang on. Yeah, goes up to 1 at the next interval, right? Or the next little piece here, the next tick mark. Then it comes back to 0 at the next tick mark. Then it comes down to -1 at the next one, and then it comes back to 0. I should still label them just for clarity and, you know, just to be precise. But that's it. Like, that's the picture of this graph. It's a sine function graph that's been shifted left by a tiny bit, by a pi on 6. And just for, you know, just to be complete, let's go ahead and find what these tick marks are. How do I do that? I say, well, the difference between each of these is a pi on 2, because I've got a full 2 pi length interval here. So if I chop it up into 4 intervals, 1, 2, 3, 4, they should each be size pi on 2. So let me take that first one and add pi on 2. That's 3 pi on 6. So that's going to be 2 pi on 6, which is pi on 3. So that's that one. Then pi on 3 plus pi on 2. So are you always going to be adding pi on 2 to find these things? Well, no. The pi on 2 is coming from the fact that I have that my interval's not, my period is not squished, right? It's not squished or extended. Okay. There's a lot of moving pieces to these trig graphs, so you want to be real careful about trying to like find patterns, because that's kind of a dangerous road. Because if you start trying to kind of be lazy and just find like these patterns, like, oh, I'll just, you know, add pi on 2 each time to find these tick marks. It's only true when the period is of length 2 pi. Why? Because when the period is of length 2 pi, then each of these little intervals is going to be 1/4 of 2 pi. What's 1/4? What's 2 pi over 4? Pi on 2, right? So that's where that's coming from. Last one, 5 pi on 6 plus pi on 2. That's 3 pi on 6. That's 8 pi on 6, so 4 pi on 3. Cool. Sample 4. Let's just practice not graphing, but just making sure we know how to find amplitude, period, and horizontal shift. Oh, and we're going to graph one period. Okay, never mind. More graphing. Okay. Oh, got to write the function. Here it is. Y is equal to 3 sine of 2 times x minus pi on 4. So there's a lot more going on in this function. Okay. I'm thinking about how to, let's see, okay. How can I use different colors to my advantage here? Let's say, first of all, amplitude is equal to 3, just straight up that number. That's going to tell you the peak and the lowest point, those extreme values of your outputs, 3 and -3. That's what they're going to be. Okay, so let me then use blue for the period here. Period is going to be like how long one cycle is, and that's going to be 2 pi over k, right? Now, what am I referencing here? Where are they? These things. So go back and look at these with this information. Clearly, 2 is playing the role of k here, so my period is pi. That's the length of one cycle of this sine. So it's been squished. It's been squished. It doesn't take a whole 2 pi to cycle through this function now. It takes only pi to cycle through the whole function because we've squished it. Squished it in half. What else does the period tell me? The period's like arguably like maybe one of the most useful things to think about maybe. So the interval, I'm going to graph on now, here we go, is of length pi. But that's all I can say now because it has been horizontally shifted to the right by pi on 4. So I don't want to say anything else about the period yet until I get down the horizontal shift, which I'll do in green. So I'll say H shift for horizontal shift is going to be right by pi on 4. So that tells me the interval, instead of just being from 0 to pi for this squished period here, instead of being 0 to pi, it's shifted right by 4, so I'm going to add pi on 4 to both of these, so it's going to be pi on 4, right? 0 plus pi on 4 is pi on 4. What's pi plus pi on 4? Think about it, it's 5 pi on 4, right? 5 pi on 4. That's the interval I'm going to graph this on. Where should each tick mark be? Well, definitely at pi on 4, right? And then 3 more, and then ending at 5 pi on 4. Can I go ahead and find them? How am I going to find them? Last time, I said, oh, if my period is 2 pi and I'm chopping it into 4 chunks, so 5 values, 4 chunks, each of those chunks should be pi on 2. So that's why I took those things off on the side and kept adding pi on 2 to them. But here, the period is only of length pi. So if I'm chopping it into 4 chunks, I'm not going to be adding pi on 2, I'm going to be adding pi on 4. I'm going to be adding pi on 4 to each of the, in increments of pi on 4 to find these tick marks. So first, pi on 4 plus pi on 4 gives me pi on 2. Pi on 2 plus pi on 4 is 3 pi on 4. 3 pi on 4 plus pi on 4 is 4 pi on 4, which is just pi. And then you should check the last one. Does it make sense? 4 pi on 4 plus pi on 4, is that 5? Yes, yes, it works. It works. That step is, honestly, it's not really about trig, right? It's about your fraction work. So if you're getting stuck there, you just gotta draw some pictures and really try to convince yourself that all that's happening is you're trying to split this interval up into pieces, evenly spaced, right? It comes down to a fraction problem. You're dividing it evenly, and then you've got to find how, once you've figured out how much each piece, how big each piece should be by dividing the interval into 4 pieces, then you got to take that piece and add it incrementally until you get all the way to that last piece there. Okay, let's put it all together. Oh, okay, yeah, I don't need, if I'm just graphing one period, it says graph one period, I'll just, you know, I don't need really much of a negative axis at all because I'm just going positive. All right, here's y. As I'm labeling things, I'll try to keep them the same color, maybe. You know, that might mess things up. Never mind, I can't do that. All right, so amplitude is 3. So that means my extreme values here are 3 and -3. My tick marks are going to be at pi on 4, then pi on 2, then, and they're pretty close together. This is supposed to be a squished graph, right? And then pi, and then finally ending at 5 pi. And notice they're all evenly spaced, right? They're all, well, that one got a little away from me, but they're supposed to be evenly spaced. Not 0 to pi. Well, actually, yeah, that one would be as well, but that's just coincidence. Anyways, the point is from here to here, here to here, here to here, and here to here, they're evenly spaced. All right, so now graphing this, it's still a sine function, so I know it's still starting at 0, right? The cosine function is the one that starts up top, right? All right, so I'm going to graph, I'm going to go all the way to the maximum for the second tick mark. Third tick mark, I'm back at the middle. Fourth tick mark, I'm down at that minimum, and then back to the middle. And there it is. Let's do a cosine one. Oh, there it is, in case you can't see it all. Oh my God, am I recording? Yes, okay, that was not a good feeling. Okay, same example, or rather same instructions as number 4. Y equals, where is it? Oh, I lost my example. Oh, I see it. I'm gonna need a bit more room, it's a long one. So y equals 3/4 cosine of 2x plus 2 pi on 3. Oh, that's a nice one. All right, so I'm going to kind of model it like the way I did the last one. Amplitude is 3/4. So that means it's going to be a little bit squished vertically, because normally a base cosine graph has amplitude 1. So this is, you know, slightly squished vertically. Okay, not much else to say there. Amplitude is like the nicest, easiest thing to point out. What about period? You may be tempted to say 2 pi over 2, right? Well, we should note that before we do anything with this, it's not in the appropriate form to identify period and horizontal shift. Go back and look at that, those notes. There they are. Should be of this form, where K is pulled on the outside of the horizontal shift happening here, right? So that's a problem because ours is not written like that. You notice example 4 was written like that, with that 2 pulled outside. We can get this one like that though. That's fine. Let's just write it like this. Just taking that internal part. I didn't need to, there's no need to write the whole thing just for this little part we're doing here. Pull the 2 on the outside, x plus pi on 3, no problem. Factor out a greatest common factor there. Cool. So now we see that K is 2, so that's the K value right there if you're looking at that that setup that I gave, you know, that I just pointed out a second ago. And this is the B value. All right. So period then is going to be 2 pi over 2, 2 pi over K, right? So 2 pi over 2. So period is going to be pi. So the intervals of length pi that's what a period means. So the interval is of length, that's an I, that's is of length pi. Well, what is the actual interval? It's 0 to pi to what? Well, maybe we should write down the horizontal shift first. Well, the horizontal shift is left this time, and I'm not looking here. It's not 2 pi on 3, right? It's over here. It's left. Why is it left? Well, because we're adding inside. When you add inside the function, it's kind of counterintuitive a little bit. I mean, it's really not if you really think about it, but it's opposite to how vertical shifting works, right? When you're adding, you're moving left. So left by pi on 3. Okay. So now come back to period here. Where is that new period? Where's the new good place to write it? Well, I should subtract pi on 3 from both of these. So I should be going, instead of 0 to pi, going from negative pi on 3 to 2 pi on 3. And I'm just going to let you figure that fraction arithmetic out right there. I'm going to ask the same question that I did for the other example. Down here, though, where should each tick mark be? Start off with negative pi on 3, then blank, 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 and then the ending at 2 pi on 3. All right. What do we add to each? What do we add in increments here to get these unknown values where the tick mark should be? We should add pi on 4. Pi on 4. Why? Because my interval is of length pi, and I'm splitting it into 4 pieces, 4 chunks, represented by 5 tick marks, right? If there's 5 tick marks, then there's 4 chunks, right? And if the interval is of length pi, chopping it into chunks of 4, that's going to be pi on 4. So I'm going to add pi on 4 to each one of these. So, what are these going to be? Let's see. Negative 1/3, that's negative 4/12 plus 3/12. So negative pi on 12, or these are no fun. Okay, I didn't want to get to the denominator of 12, but oh well, that's what we got. The next one, I'm adding pi on 3 to this, so that'll be, no, not pi on 3, pi on 4, right? So I'm adding pi on 4 to this. Pi on 4 is 3 pi on 12, so okay, good. That gives me back to pi on 6. I'm letting you do this, right? You can pause the video, do these on the side. And then pi on 6, let's see, 2, 3, 5 pi on 12. And just to make sure I got my fraction addition right, let's see, another 3 pi on 12 added onto this would be 8 pi on 12, which would reduce to 2 pi on 3. Cool. So my graph does go into the negatives a bit, so I'll have more of a negative axis here. And then it's a bit squished. I'm going to represent that with a 3/4 there and a negative 3/4 there. This one should be a little bit higher up. All right, my values, let's see, my x values are they're at, so the first two are still negative. This one's barely, like, it's like right there, right? In fact, I'll even put them green so we know where they are. That's negative pi on 3. There's the negative pi on 12. There's the pi on 6. They should be evenly spaced. So there's 5 pi on 12, and then finally 2 pi on 3. And I'm not writing them because they're just too squished, right? It's gonna be a mess. So, but just know that they're going in order. Here's the list of them here, right? All right. So here's my. Oh wait, before I get going here, it's a cosine function. I almost started down here at 0, but remember, cosine function starts at top, and then it goes middle, and then it goes bottom, and then it goes middle, and then it goes top again. So it's not really like a U or V shape, but It's the point. The point is it starts up top. Like that. There we go. That's one period of it right there. Cool. Let's just graph that one just to see it better. So 3/4 and then cosine of 2x plus 2 pi over. If you're ever graphing in here, if you just type pi, it'll automatically change it to pi, by the way. Oh, excuse me. Now, what is the interval where we graphed? Because we only graphed one thing. There it is, negative pi on 3 to 2 pi on 3. That's exactly where we graphed. So this point right here should be negative pi on 12. Ah, it is. The next point where it reaches that minimum should be, what was it? Pi on 6. Nice. And then 5 pi on 12. So those intervals, or rather those little tick marks on my x-axis are correct. So we only graphed this interval here. So so you can see. So we just graphed between these dotted lines here. Oof, there we go. One period of it, but of course it's infinite, right? All right. How does it compare to a base cosine graph? Well, pretty different, right? It's pretty different. First of all, it's squished vertically, so you'll see the purple cosine graph is going higher and lower, but not by too much, right? Because the amplitude is, there's not a huge difference in amplitude here. This one is, the base one is amplitude 1, and the one we graphed has amplitude 3/4 or 0.75. Maybe a bigger change is that it's been horizontally squished. So you see it's like it's rotating faster because it's been squished, and also it's been shifted left. It's been shifted left. So if I took that left shift out, what would that look like? So sometimes it's fun to just play with these just to see what they look like. So here's one that is just, it has a lower amplitude and it's been squished horizontally because that ×2 is still in there. So this one has period pi. So you see it'll do a whole rotation right there from 0 to pi. Whereas the purple graph is going to need a whole 2 pi, 0 to 2 pi to do a whole rotation. Okay. It's good to just go play with them to get a feel for how the graphs are acting. All right, what's next? Oh boy, yeah, we're going to start talking about the other graphs, right? Cosine, no, not cosine, cosecant, secant, tangent, and cotangent. Where are my notes? Give me 1 second, I gotta find my notes. Okay. Let's consider cosecant first. So let's say y is equal to sine of t, from the going back to the unit circle definition, with t being an arc length / radian measure of angles. Then on that unit circle, so here's t, right? It's t value, arc length t as well, right? The same thing on the unit circle. And there's a little coordinate point where it ends at xy. And the sine function of this angle t literally outputs that y value. That's what the sine function does, right? Okay, what does the cosecant function do? Spits out 1 over y, right? It's the reciprocal. So cosecant of t is equal to 1 over y, the reciprocal. Okay. Where are we going to have domain errors? We will have, or domain issues, I should say, we will, when y is 0, right? But when is y 0? For what t values over here on the unit circle, for what t values is y 0? Y is going to be 0 on the x-axis. What t values is that? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and going reverse, 0, negative pi, negative 2 pi, negative 3 pi, increments of pi, right? We will have domain issues for cosecant. Let's say spell it out, cosecant, at, and be a bit more vague here, input values, because we're going to go back to what the book wants to do and putting x for domain, which is super confusing because it's not that x on the unit circle, right? Okay, we'll have domain at input values of n pi for n in the integers. So, you know, just any integer, pick an integer like -3, -3 pi, we're going to have a domain issue there. 0, they're going to have a domain issue there. 2 pi, yeah, we're going to have a domain issue there. At all whole and negative whole number pi values, we're going to have domain issues for cosecant. Okay, that's fine. That's fine. We can still graph. We can graph stuff with domain issues. We did it in 112, right? So we can do it here. So what's going to happen with this cosecant graph? Okay, let's consider a sine graph first, because they're very much related. One is a reciprocal of the other, right? So let's get a nice big sine graph going here. You can probably skip through this part because I'm just graphing. Shoot, that's fine. Okay, and then let's put a 1 and a -1 there. Okay, sine starts here, goes here, 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 and here. There. Okay. And etc. That might be the ugliest sine graph ever. Okay, so what is cosecant going to do here? Well, cosecant is supposed to be 1 over y, right? So, goodness, this really is like terrible. Let me just emphasize where this thing is supposed to be crossing. All right. So first of all, cosecant is going to be matching sine at the inputs of pi on 2, right? At inputs of pi on 2, because sine of pi on 2 is just 1, right? And if the output is 1, what's 1 over 1? Well, it's still 1, right? So cosecant's still going to be matching. Cosecant's still going to be matching here. What happens as we try to get close to 0? As we try to get close to t equals 0, but that's going to be a domain issue. So what happens as we get close to 0 for the cosecant function? Well, y is going to tend to 0, right? Because as t is closer to 0, the y value gets smaller and smaller, right? Thinking on the unit circle over here. As t gets smaller and smaller, the y value gets smaller and smaller, right? It's getting lower and lower and lower and lower. If you're dividing by a very tiny number, what did that do for reciprocal functions? Remember that from 112, like 1 over x squared, stuff like that? As you plug in very, very tiny numbers into a denominator, didn't that make the functions explode to infinity, right? Like 1 over, 1 over 0.000009 is going to be the same as just like 9 million or whatever. I don't know how many zeros I said, but the point is when you divide by very tiny numbers, the result is a very large number. So what's going to happen as we try to get very close to the zero, our cosecant graph is going to explode off to infinity. The same thing's going to happen when we try to get very close to pi. When we try to get very close to pi over here, again, the y value is tending very close to zero, still positive, very close to zero, and it's going to explode off to infinity this way. Now, what about down here at -1? When sine is -1, cosecant should be 1 over sine, 1 over -1. It agrees there at that value. What if I try to get very close to pi from the other side, coming from the opposite direction? So imagine like a t value here and getting very, very close to pi here, getting very close to pi, an output of 0. It's still going to explode to infinity, but now things are negative, right? The y value, when you're down here, the y value is negative. So it's going to explode to negative infinity. Same thing's going to happen on the opposite side when you try to get close to 2 pi. Try to get close to 2 pi, it's exploding off to infinity, but everything is negative, so it's looking like this. All right. Oh, God, my voice. So let's see some better pictures. Okay, let's go to Desmos. So, and I will spare you from my terrible graph here. All right, I do want sine because it's a nice reference. And now what I want to do is mark those asymptotes where cosecant behaves badly. So I'm going to say n pi, and I think I can add a slider. What do I want to do here? Hang on, let me figure this out. Let's see. X equals. Oh, no, that's not what I want. Okay, I'm going to do x equals pi. I'll just do a few. X equals negative pi. Definitely 0. 0 is going to be one of them. And then I'll just do the 2 pi's. I'm not going to list all of them, obviously. There's infinitely many. Wouldn't be able to list all of them. All right, and now I'm going to go here. I'm going to make them all red. Red dashed lines. Cool. So these are where I should expect the asymptotes to be, right? Where sine is 0. Look, the output is 0 at all these, right? And since cosecant is 1 over sine, then I should expect bad behavior around these 0 values. So let's see what happens. Cosecant x. There it is. So what I've graphed for you is just these two, one period of it. So one period of cosecant is going to be when you've got a whole top loop thing. It's not a loop. This part here and a part that shoots off to the bottom. So it still has period 0 to 2 pi. You got to go from 0 to 2 pi to get a whole thing, to get a whole cycle of cosecant. But there it is. It seems very strange when you look at it, but it's just a consequence of it being the reciprocal of sine. Look at that. It's kind of nice. It's kind of nice. All right. All right, so let's write down some notes about cosecant. Get my ugly graph out of here. Let's say it's just like sine, it has period 2 pi. And a good interval, again, I'm pointing out this like good interval to graph it on, is 0 to 2 pi, just like sine and cosine. So no big surprises there. What else? It has vertical asymptotes at this time I'm listing out some of them instead of just saying NPi, just to give you the idea like what's happening here. Those are some examples of some of its vertical asymptotes. Here's an interesting point to make. Its local minimum value agrees with the sine graph's local maximum value, and vice versa. Vice versa here, meaning the local maximum value of cosecant will agree with the local minimum value of sine. Now that's a weird point, but let me just, you know what I'm talking about when I point at it. Let me show you what I'm talking about here. So just considering these two here, these two here. Right here, for the black sine x curve, the local maximum right here is 1. And for the blue curve in this point, its local minimum is 1. So the local maximum of sine at this point is agreeing with, that's where they overlap. That's the one and only point where they touch, right? The highest point of sine becomes the lowest point of cosecant. Oh God, did I say cosine earlier? If I said cosine, I meant cosecant, sorry. And then same down here, the local minimum of the sine graph, the lowest point of the sine graph around here agrees with the highest point of the cosecant graph, at least in this little area, right? So they're touching there. Okay. Cool. Did I say it has period 2 pi? Yes, I did. All right, let me check my notes, see if there's anything else I left off. Nope, let's talk about secant now. Secant. So consider x is equal to cosine t. So remember, going around the unit circle, if this is a t arc ending at a point xy, then literally, so this is a t angle and a t arc on the unit circle, the x value literally is given by cosine of that angle. And secant is the reciprocal of cosine, 1 over x. 1 over x. So we should expect a similar thing happening here with vertical asymptotes or domain issues where x is 0. Well, rather, yes, but what t values, right? I'm sorry, I'm keep glancing back at the way I wrote the other one. I just want to like write it similarly to how I wrote the notes for cosecant. And input values, so this time, where is x going to end up being 0? It's going to end up being 0 on the y-axis, right? Here and here and here and here and here on the y-axis. What angles are those? Well, pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2, right? So how do I notate that? I say pi on 2 plus, and then integer multiples of pi on 2. So with n being in the integers, with n in the integers. pi on 2 plus n pi with n in the integers. So for example, like negative 3 pi on 2, just odd ones, right? That's kind of the point, they're odd. Negative 3 pi on 2, negative 1 pi on 2, positive 1 pi on 2, positive 3 pi on 2, etc. But not 0, right? It's no problem at 0. No problem at 0. Okay, cool. All right, we're going to see a very similar thing happening here. Here goes my attempt. Here's 1, negative 1, and then pi on 2, pi, 3 pi on 2, 2 pi. And I'm going to graph cosine here. So cosine, remember, is starting up top like this, coming down, and then here and here, and then up here. So there's one period there. Back this way. There we go. There's a sort of good cosine graph. 2 periods of it. What is secant going to look like? Well, secant, just like cosecant, is going to agree with the graph at those kind of extreme values there. It's going to agree there. But it's going to have these asymptotes at the pi on 2 values, where cosine hits 0, right? Where everywhere where cosine hits 0, it's going to have these asymptotes. Cosine is positive up here, right? Like, look, the red line is literally above the horizontal axis, so cosine is positive here, so secant should be positive. So that one's kind of getting stunted there because of the writing up here, but then this one would be like this. Don't worry, I'm going to show you a Desmos picture as well. And then this one will be like this. Okay, so it's super similar. I mean, it is the cosecant graph, just phase shifted or shifted horizontally by pi on 2. The same way that cosine and sine are related, right? I can build a cosine graph just by shifting a sine graph left by pi on 2. I can take a cosecant graph and shift it left by pi on 2 and get a secant graph. If you're recognizing that these are just shifted versions of each other, then you're getting the point. But let's just go look at one real quick. So let me erase all of this. Let me go ahead and plot down my cosine x graph. Go ahead and write a few of these asymptotes. So give me 1 second. X equals pi over 2. Pi over 2. X equals negative pi over 2. Okay. It's good. Oh, and then let's put the secant graph in. Boop. There it is. Oh, let's make it a different color. There it is. There's the secant graph. I mean, it looks just like the cosecant graph, right? Just shifted over. Its asymptotes are in slightly different locations, but they're spaced evenly as well. Now, I want to say some notes about this, but while we still have this picture up, I want to point out one of the things I'm going to write down, which is that a good interval is not going to be 0 to 2 pi. It still has period 2 pi, and I'm going to write that down in a second. It still has period 2 pi because to do a whole cycle, like one of these and then one of these, that's going to be a whole 2 pi. But where is it going from? To get this guy and then this one down here, I need to go from negative pi on 2 to 3 pi on 2. Ooh, I just realized I need to make an adjustment to something else I said, but it's a small thing. That's okay. All right. So a good interval to graph this on, unlike the other 3 functions we have so far, is not going to be just 0 to 2 pi. It's the same length, but we're going to want it from negative pi on 2 to 3 pi on 2. Now, why? Why does it matter? Why can't I just graph it from Let me put some bars here for you. X equals 0 to x equals 2 pi. Why not just graph it from there to there? I'm gonna make these black to stand out. So why not just graph these, like this little half angle, or this little half curve, and then this full bottom curve, and then the other half of the top curve, like between these two black lines. Why not just graph that? Well, because you don't really want to break up the period like that of the you don't want to break up the curves. You don't want, it's just not good form. It's much better to graph this from here to here to get a full top curve and a full bottom curve instead of breaking that top curve in half and doing, you know, left and right like that. Okay. Notes. I'm trying to preserve my voice because I'm getting like a sore throat and my voice is getting real sore talking. Oh, dang it. I did the thing again that I didn't want to do. Okay. Was distracting myself. A good interval to graph this on, you don't want to put brackets around these because these are asymptotes, right? For this graph, it never touches these values. So really what I should say to fix this is just put parentheses, negative pi on 2 to 3 pi on 2. And go fix that for the cosecant graph too, right here. That's just, I mean, honestly, like we could have gotten away with that the whole time. It would never really matter, but just for my, I mean, it's bothering me to see it written down wrong. So there we go. There it is. What else can I say? It has vertical asymptotes at odd values of pi on 2, right? Odd multiples, rather, of pi on 2, etc. And its local minimum value agrees with the cosine graph's local maximum value and vice versa. So the same kind of point that I made last time, it like lines up really nicely with the cosine graph at those highest and lowest values. Cool. I'm moving my notes fast here because you can just pause, right? If I'm moving it too fast and you didn't get all that written down, this is a recording, so you can just pause. All right, let's graph each function. Here's part B. There it is. Oh, okay, similar. Oof. Oops. All right, part A. how do we go about graphing this? They don't have amplitudes. You notice that they don't have amplitudes because they blow up to infinity and negative infinity, so they don't have like bounds on their y values, but they do have sort of bounds. They have like a lowest, like they have like a local highest and lowest value. That's what that 1/2 is going to tell us. So I can go ahead and like start my graph here, but I mean, I've got a lot of work to do before I can actually start writing down the graph. But I can note that this value 1/2 and also at negative 1/2 is going to be where the where it bounces off of. So down here somewhere, bouncing off of these values. Normally they would just bounce off of 1 and negative 1, right? But here it's bouncing off of 1/2. And where's that coming from? It's coming from that number up front. So it's not the same as an amplitude, but it is the amplitude of a graph y equals 1/2 sine x, right? So you could graph like a 1/2 sine x function and then bounce it off of there. And in that case, you could describe the sine graph as having amplitude 1/2. But when you're talking about a cosecant graph, you do not say that it has amplitude. Okay, that's just terminology there. Also, I can see that there's something going on with its period, right? It's got a compression factor because horizontal compression factor because of that too. And I already said that they have the same period as here. Let me get that. It's period 2 pi cosecant. Period 2 pi, and we're going to graph it on 0 to 2 pi. So period for this part A, this is still part A, right, is going to be 2 pi over that k value, so 2. So this one is going to have a squished period, 0 to pi. So instead of graphing from 0 to 2 pi, we're going to be graphing from 0 to pi, so maybe I can go ahead and slap pi out here. Now, the next question is where are the asymptotes? That's going to be a huge question for these graphs that have asymptotes, is where are the asymptotes? Well, how do we say this? There's a few different ways. Well, one way to say it is that since we know the period is pi, and we should have two intervals within that period split by an asymptote. So what am I saying there? I'm saying, like, I know that within this period of pi, we should have one part going up, right? And then an asymptote, and then one part going down like that, right? We should have something like that. So if it's pi, if it's length pi, then where is that central asymptote? First of all, the two outer asymptotes have to be at the edges of that interval. So they have to be at 0 and pi. Okay. But where's that central one going to be? Well, maybe that, you see what I'm getting at? It's going to be kind of easy to find. It should be right down the middle, right at pi on 2. Going to be right down the middle. You just take that period and split it right down the middle. That's because it only achieves one central asymptote. If you're graphing one period of cosecant or secant, you're going to have one asymptote splitting your interval right down the middle. So just take your period and divide it by 2. And that's where your central asymptote is going to be. Of course, there's 3 altogether, right? There's 2 on the edge, but those are easy. They're on the edge, right? They're at 0 and pi. And then you're going to have that central one right there. Cool. And now all I do is I say, all right, I know that the cosecant graph should, it's like lowest value right here, like lowest local minimum should be at that 1/2 value, and then it's going to blow up to infinity like that and like that. And the other one should be down here at negative in the other interval, the other across the asymptote here, right there, local maximum value at negative 1/2, and it's going off to negative infinity. There you go. There it is. That's one period of it. That's one period of it. Okay. So should we graph it in Desmos? Let's see what it looks like. Oh, I'm not sharing my screen. Hang on, let me just finish writing it down. Okay. Whoops. There it is. All right, so that looks crazy, but all we did is, I'll even make it the same color we drew, or I drew it. We did just here from 0 to pi, rather. So here I'll say x equals 0 and x equals pi. So there's the asymptote right there at the edge, and then there's a central asymptote at x equals pi on 2, right down the middle. And they're hitting those values of 1/2, or well, rather 1/2 and negative 1/2 for the y values. You see that happening there too. Cool. Okay, what about this part B monstrosity here? Let's have to go get some more paper. That's okay. So part B. Well, first thing I should note, I'll just go ahead and rewrite it. I'm going to write it in orange. Y equals 1/2 cosecant. There's definitely a shifting factor in there, right? But I should note this. Always remember that if it's of this form, you got to factor out that number. Whoops, that's a 4. That's a 4 under there. You got to pull that 2. Oh, wait, no, it's not a 2. Yeah, it is. Yeah. Whoa, I just had a brain fart. Okay, yeah, pull a 2 out. So it becomes x plus pi on 4. When you pull a 2 off of 1/2, you're left with a 1/4. Let me rewrite that because that 4 became a disaster. It's definitely pi on 4. There we go. Just think about it. If you sent the 2 back in, it would be 2x plus 2 pi on 4, which would yield pi on 2. Okay, so thus we have the same function that we had last time, same as part A. It has the same period and everything, period of pi, because you would have 2 pi over 2, right? Same as part A. Except shifted left by pi on 4. All right, cool. What does that mean? That means we're going to draw this graph. Oops, draw this graph. Put that 1/2 there, put that negative 1/2 there. All right. I'm going to shift. What were the defining features that helped me plop this cosecant graph down? The asymptotes, right? The asymptotes. Shift those asymptotes left by pi on 4. How do you do that? Well, the first one was at 0. Shift it left by pi on 4. Where's it going to be? Oh, what color did I use for asymptotes? It's going to be at pi on 4, right? Well, no, it's not. It's going to be a negative pi on 4, right? Negative pi on 4. Okay, now the next one is right in the middle at pi on 2. Shift that left by pi on 4. What do you get? Pi on 4 again, right? A positive pi on 4 this time. And then finally, the last one was at pi, and I'm shifting that left by pi on 4. So they're evenly spaced. There's a half pi in between each one, and that's going to be 3 pi on 4. No, yeah, 3 pi on 4. There we go. How did I get those? I just took where my asymptotes were at 0, pi on 2, pi, and subtracted pi on 4 from each one, shifting left by pi on 4. And then here we go. It's going to be right here. Oh, wait a second. Hang on. Am I making a mistake? No, we're good. Okay. The only thing maybe I'll point out is that I'm just to write it down. I'm graphing on negative pi on 4 to 3 pi on 4. I mean, that's in that you see that here. Negative pi on 4 to 3 pi on 4. Okay. There we go. And then this one in the other section here, the other interval, there it is. All right. Okay, let me grab some more paper. And we'll graph some secant functions. And then we'll move on to tangent and cotangent. It's going to probably be a longer than 90-minute video. Okay, y equals 3 secant 1/2 x. Okay, so I know that should I go ahead and draw my graph? Would that be getting too ahead of myself? Well, maybe not. I need a fairly big y-axis just to, or I want to call it a vertical axis, but whatever, the book calls x and y, right? And I'll go ahead and put a 3 here. That's going to be like where I bounce the graph off of, and then -3, that's where I'll bounce it off of in the bottom. There is something going on with the period of this graph, right? Because of the 1/2 inside. So period will be equal to 2 pi divided by 1/2, which is going to be the same as 4 pi. So this one is stretched out to 4 pi. It's still going to look like, like a top curve and a bottom curve, but it's going to have to go all the way to 4 pi to achieve that. Now the question is, do I graph on 0 to 4 pi, or do I graph on, where do I want to put the question? Because I don't want to write over the space. I guess down here. Or what's the other option? Well, recall for the secant graph, where is it? A good interval to graph it goes into the negatives a little bit just because of the shape of it, right? You don't want to break up that top curve. So negative pi on 2 to 3 pi on 2. How does that correspond here? If I've doubled the interval length, right? I've doubled the interval length. So instead of just taking it and scooting it back a pi on 2, I'm going to scoot it back, whoop, a negative pi, a whole negative pi. So instead of going from 0 to 4 pi, I'm going to go from pi to 3 pi, negative pi to 3 pi. Okay, so I'll go ahead and mark those things. That's going to be where my first two intervals are. There's negative pi, and then there's going to be, let's see, pi, 2 pi. So 3 pi is all the way out here. By the way, that's where my two intervals are. No, not intervals, sorry, my two asymptotes, right? I'm going to have to find that central asymptote, but where should it be? How long is this interval? 4 pi. So where's the central one going to be? 2 pi, right? This picture is not to scale, sorry. So there's that central one, 2 pi. Wait. No, it's not. Oh my god, I just messed this up. It's not going to be a 2 pi. Oh. It's going to be a pi, right? Ugh. Because I'm not going from 0 to 4 pi. If I was going from 0 to 4 pi, then the central thing there would be 2 pi. But I'm going from negative pi to 3 pi. What's the central value between negative 1 and 3? Well, it's 1, right? It's 1. So can I just do and just call that a pi? Will you believe me if that's pi? It's not quite a good picture. Looks like we'll be relying on Desmos again to get a decent picture here. Okay, so this is what I need though. This is all I need. I need to know those values it's going to bounce off of, and I need the two outer asymptotes. If it's secant, I need to think about scooting it back to not be splitting up that top curve. And I find that central asymptote, and now I just go ahead and say, boom, right there. And then down here should be at that -3 value and going like that. That is so bad. Let me go to Desmos and show you what's going on. Okay, get rid of all these. 3 secant of 1/2 x. And why aren't I seeing anything? Because you see, I'm not at the values of 3, so I need to zoom out. There it is. And we went from x equals -pi to x equals 3 pi. There's that one period that we did from here to here. This curve, and then that central asymptote is at x equals pi. Right down the middle. Okay, that's enough of cosecant and secant. Let's talk about tangent and cotangent. And let's see if we can get through, now that we kind of have a feel for these, well, actually tangent and cotangent do behave a bit differently. So let's see, maybe we do need to be careful about these. Okay, coming back to the unit circle. Oop. There we go. Coming back to the unit circle with some t arc length subtended by some angle t terminating at a point xy. How does tangent relate to this stuff? It takes in tangent of t, or it takes in an input of t, and it spits out a y over x value, the ratio of those two sides, or those two coordinate points or values. Okay, so we're going to have domain issues where x is 0 again. Okay, so that's like the, which one was that, like secant. So it's going to have the same asymptotes as secant. Namely the pi on 2 values, odd pi on 2 values. Okay. What is going to be the period for tangent? So for cosine and sine, they need an entire revolution, 2 pi whole revolution around the unit circle to hit every value. That's why their period is 2 pi. Tangent does not. Tangent is going to hit every possible value it can in just a half revolution. Why is that? Well, think about how, let's say, how sine works. Sine is hitting values, only positive y values on the first half rotation. Right? It's getting all the positive y values. It has to go all the way back around down here to get negative y values. So it needs a whole rotation so that it can get all of its positive and then negative values. Cosine, how do I say this? And then here. Cosine gets its positive values here where x is positive, and then it gets some of its negative values. But then, oh, wait a second. I'm confusing myself. You know what, I'm gonna have to come back to that. I am super tired and out of it. But anyways, just for now, let me just leave it at that. Cosine and sine need a full revolution around the unit circle to hit every value. That's why their period is 2 pi. Tangent is only going to need, and cotangent actually, are only going to need a half revolution. In other words, long story short, period is pi. In a natural or a good interval to graph on, because it kind of has the same issue as secant, where it gets cut off if you graph it from 0 to pi. So a natural interval to graph it on will be negative pi on 2 to pi on 2, which is of length pi, right? That's still period pi. Just taking it, instead of going from 0 to pi, we're going from negative 1/2 to 1/2, negative pi on 2 to pi on 2. What's it going to look like? I'll just graph one period here, and then we'll let Desmos take over to graph. So now I'm going to graph y equals tangent x. So I'm changing variables to a domain variable of x. Okay, so I know it's confusing, but this is what the book insists on doing. Okay, so we're going to have, just say pi on 2 right there. Negative pi on 2 right there. So that's asymptotes. All right. What is tangent when the input is 0? I'm going to do this in blue. What is tangent when the input is 0? Well, it's right here. Y is 0, so the top is 0, so it's 0. No domain issues at 0, right? What happens as we try to let the value, the t value, if I'm thinking about it in terms unit circle with input t, like up here, is t gets very close to pi on 2, so very close to pi on 2, then that denominator x is getting very close to 0, sending this output to infinity. So like that. Okay, so far sort of like a secant cosecant in that it's exploding off to positive infinity. What about on the other side though? So does it do like like that? What does it do? So as we go from, where are we going? From 0, so from 0 to negative pi on 2, so now we're trying to go this way. Whoops, trying to go this way. I guess I could draw an arrow. 0 to negative pi on 2, what's happening? Well, x is getting very close to 0 again, right? X is getting closer and closer to 0, but it's all negative, right? The x is not negative. The y values are negative, so everything outputted down here by the tangent function is negative. So we're not blowing up to infinity again, we're going to negative infinity. That's the tangent graph. That's the tangent graph. And it's going to keep doing that little dance repeatedly. Let me show you in Desmos. Where's 0? There it is right there. Yep, so we see these asymptotes happening as we try to let x get closer and closer to pi on 2. By the way, what is pi divided by 2? It's like 1.57, right? So as we try to let this input get closer and closer to 1.57, it's just going to blow up to infinity. And same on this side, as we get closer and closer to negative 1.57, it's going to go off to infinity. It'll never touch that negative pi on 2 value, or pi on 2, or any other multiple of it. As you can see, it's infinite. Whoa, all right. Cool. So there's the tangent graph. Okay. Any notes about it? Well, I think I've noted everything here, the natural interval, the period. What else did I write down? There's no kind of nice interpretation, you know, connecting it to sine or cosine, really, not like cosecant, secant had, right? So it's kind of its own graph. All right, how about cotangent of t equals x over y? So again, with the unit circle picture, here's t, angle t. So it's going to be undefined, so it's going to have same asymptotes where y is 0, so same asymptotes as cosecant. Oops, as cosecant. I didn't mean to put a space there. Cosecant is one word, and what were they? They were the pi values, like multiples of pi. So negative 2 pi, negative pi, 0, pi, 2 pi, etc. Cotangent's going to have the same period as tangent, so period is pi, and a natural interval will be just 0 to pi. No, wait. Hang on. Am I going crazy? 1 second. One second. I need to check something. Oh, goodness. Come on, Desmos. There we go. Yeah. Yeah. Okay, sorry. I am so out of it. I need to sleep. Okay, a natural interval is 0, open parentheses, 0 to pi. Unlike tangent, which you had to scoot back to get a natural interval of it. All right, let's talk about what it's going to look like. Here's pi. I already know there's going to be asymptotes at 0 and pi. Question is what's happening in between. So right here is pi on 2. That's going to be a nice thing to note here. Pi on 2 there. Okay, at pi on 2, what happens to this? At t equals pi on 2, x is 0, so we're getting a 0 right in the center. Okay, no problem. Now, as we go from pi on 2 to pi, so if we're going from here to here, what is happening to the y value? The y value is getting very small, and it's positive, but it's getting very small, so this fraction is going to blow up to infinity, to positive infinity in particular. Hang on, something is, I'm not doing this. I'm still tripping a little bit. No. Hang on. That's not right. I didn't draw that right. Oh no, I wish I could just pause the video and figure out what's messing me up here. Oh God. Ugh. Over here, yes, we are tending to 0 and y is positive, but x is negative, right? So x over positive, that's going to be negative, right? So it's blowing off to negative, blowing up to negative infinity, not positive. Sorry, dumb mistake. Okay. So going from pi on 2 to pi, the y value is getting smaller and smaller. The x values are negative over here. That's why we're going off to negative infinity. Now going backwards from pi on 2 back to 0, that's going this way, right? What's happening this way? Everything's positive, all right? We're in the first quadrant, and the y value is going to be getting smaller and smaller, sending this fraction off to infinity. Sorry about that ugly picture there. So it looks very similar to the tangent graph. It's just like scooted and flipped, right? Which we expected because cotangent and tangent are reciprocals of each other with similar domain issues. So let me go ahead and show you a graph of cotangent. I'll show you where we graphed it to, because this is kind of a lot to look at here. So I graphed it. Let me change the colors. From 0 to pi, that is a nice natural interval there. So this blue line is what I graphed as well. This one, that's one period of it. All right. So we got through all that. Sorry, I'm just glancing through. Okay, all these ideas together with those notes I sent you guys about function transformations. It's going to put all that together. That's going to be what you need to know for this section. So I think probably next time I'll, what even section is this, 6.4? Yes, and we have, how many more days before exam? Is the exam the 24th? Yes. So I'll spend the 22nd just kind of doing more examples and also going over the tiny bit of 6.5 that I want to go over. And that'll be it. All right.